In this video, we'll go through some examples to familiarize ourselves with the use of transformer equivalent circuits. In this example, we have a 50 kVA step-down distribution transformer that is not connected to any load. The primary winding, or the high voltage winding, has a leakage impedance given by this. So this is R sub 1 here, and this is X sub 1. On the low voltage winding, or the secondary winding, its leakage impedance is given by this. So this is our R sub 2, and this is X sub 2. At rated voltage and frequency, R sub C is given by this, and X sub M given by that. So in A, we're asked to determine the exact, or to draw the exact equivalent circuit referred to the high voltage side, or the primary side, and the low voltage side, or the secondary side. For B and C, the transformer is connected to a source, and we're asked to determine the magnetizing current and the coreless component current of the exciting current, and C, the secondary winding terminal voltage. Take note that the secondary is not connected to any load. So here's the solution. So here is the equivalent circuit, the exact equivalent circuit of the transformer that is referred to the primary. So we simply write down the values of R sub C and X sub M, R sub 1 and X sub 1. So R1 and X1 here is written as the impedance Z sub 1, and X sub 2 prime is the reactance of the secondary winding referred to the primary. Likewise for R sub 2 prime. And these two are also expressed in terms of the impedance Z sub 2 prime. So to get Z sub 2, we simply multiply Z sub 2 by the square of the turns ratio. So here's the turns ratio. So it is equal to 10. For so R sub 2 prime there is this one, and X sub 2 prime is this one. Now I sub 2 prime can be computed from this formula, and given turns ratio, it means that I sub 2 prime is simply 1/10 of the secondary current, while V sub 2 prime is 10 times the voltage at the secondary output. So this is the exact equivalent circuit of the transformer referred to the low voltage side, or the secondary side. So we simply copy X sub 2 and R sub 2, while we refer R sub 1 and X sub 1 in the primary, and that will give us this value. We also refer R sub C and X sub M to the secondary, and that will give us these values. So this is the computation for Z sub 1 prime, where this one is R sub 1 prime, and this one is X sub 1 prime. We also have the computation for R sub C prime and the X sub M prime. For I sub 1 prime, we can get it using this formula, and that will give us 10 times the secondary current I sub 2. And for V sub 1 prime, we can again use this formula, and that will give us 1/10 of V sub 1 of the primary. For B and C, this transformer is connected to a voltage source. So the primary winding is connected to this voltage, but there's no load connected to the secondary winding. So that means that I sub 2 is 0, and that will make I sub 2 prime 0 as well. So that means that these terminals here is actually an open circuit. So here we're tasked to determine the exciting current and its components I sub C and I sub M, and also this voltage here. Um, so since this is an open circuit, or I sub 2 prime is a 0, that would mean that the exciting current is equals to I sub 1. That is the current drawn by the transformer. We can compute I sub 1 by dividing the applied voltage. So we assume this to be angle 0 degrees by the total impedance, which is this one, plus the parallel combination of R sub C and X sub M. Okay, so what is this parallel combination? So that would be 631.6 plus J. So therefore, if we compute I sub 1, that will give us 0.54 at a phase angle of 81.8 degrees amperes. Okay, so this is also our exciting current. Now to get I sub C, we can use the current divider technique. Here this is equals to um, JXM over RC plus JXM. And this will give us 0.078 amperes. And for I sub M, we can do the same. So that would be 0.54 amperes. Okay. Uh, so how about V sub 2 prime? So V sub 2 prime is actually also the voltage across here. So let's call this V sub P, and that voltage is equals to I sub V times the parallel combination of R sub C and XM. Okay, so that would be this times and that will give us, okay, so that is our V2 prime. So notice that the value of V2 prime is close to the applied voltage, uh, including its phase angle, so that is an indication that our computation must be correct. In this problem, we repeat example number 4, B and C, but using the approximate equivalent circuit referred to the high voltage side only, or that means referred to the primary winding only. So this is the approximate equivalent circuit referred to the primary. So what we did there is simply to move the shunt circuit in front and parallel to the voltage source. So this is the shunt, and that means the exciting current can easily be determined, and that is 2400 divided by the parallel combination of R sub C and X sub M, which is this impedance, and that will give us an answer of 0.54 at an angle of minus 81.8 degrees, which is roughly the same as what we got in the previous problem. Hence, this shows that the approximate equivalent circuit can be used as a replacement of the exact equivalent circuit. So we can determine from this I sub C and I sub M as well in a similar manner, and you will get similar results, almost similar results as the one we got earlier. Now, V sub 2 here, however, is slightly different, because take note that since this is now in parallel, the shunt circuit is now in parallel with the source, and we said that V2 prime is equals to this voltage. That means V2 prime is actually 2400 volts. Okay, since this is an open circuit here. So it's a bit off, although still close to the applied voltage. In this problem, we repeat example 4, where the transformer is connected to a voltage source, but this time it is connected via a transmission line with an impedance that is equals to this, Z sub F. Also, the exciting current is assumed to be zero, that is, we ignore the core losses and the magnetizing current of the transformer. Also, the secondary side of the transformer is connected to the load that has a power factor equals to 0.8 lagging. So the question is, what is the voltage at the load side? The voltage V sub 2, the full load efficiency of the transformer, that is the efficiency of the transformer while it's operating at the rated load, and the voltage regulation of the entire setup, that is transformer and feeder combined. So let's proceed with the solution. Here is the setup again, with the transformer replaced by its exact equivalent circuit. So this is the exact equivalent circuit of the transformer, and the load is attached to that equivalent circuit. Likewise, the feeder is also attached to the equivalent circuit. Take note that the load is drawing rated current from the transformer. Uh, that would mean that the transformer is supplying rated current to the load. So how do we get that rated current supplied by the transformer? If a transformer is supplying rated current, that means that it is operating at its rated kVA. So that means that 50 kVA, which is the kVA rating of the transformer, must equals the rated current of that transformer, which is the output current at the secondary, times the rated output voltage of that transformer. So as specified, the transformer rating is 2400 at the primary, and the secondary is 240 volts. So from that relationship, we can extract the rated current that is being delivered by the transformer. So this is the rated current. Now, let's assume for this problem that we make the voltage of the load, the voltage V sub 2, as our reference phasor. So therefore, we can write the phasor V sub 2 as equal to its magnitude with a phase angle of 0. So since the load is 0.8 power factor lagging, that would make the current uh, to the load, the phasor of that current as equals to this phasor. So the rated current has a phase angle of negative 36.87. This is taken from the given power factor of 0.8. To solve for the voltage V sub 2, we can refer the secondary winding parameters uh, to the primary side. So here, this is the secondary impedance referred to the primary, and this is the load current and voltage also referred to the primary side. So the I rated becomes I rated prime, and V sub 2 becomes V sub 2 prime. We can compute for the I rated prime using this formula. So that would give us that I rated prime. We can also compute for V sub 2 prime as a function of V sub 2, and that should give us this expression. Observe that the feeder impedance, the primary winding parameters, and the secondary winding parameters referred to the primary are all in series, and therefore we can combine them. That should give us this simple circuit. Take note that if we can find V sub 2 prime, you should be able to solve V sub 2. So it appears that this is a simple problem, but take note that we don't know the phase angle of V sub f because we have already assumed V sub 2 as our reference. So therefore, we cannot say that V sub f has a phase angle of 0. So what we can do here is um, we can draw the phasor of the quantities involved. So V sub 2, the voltage V sub f, and the voltage drops across the resistive and inductive components of these elements. So let's do that. First, we draw V sub 2 prime. So since it has a phase angle of 0, we can draw that as a horizontal line. Next, we draw the I rated prime. So we know this current already. So since it is derived from I rated and I rated is lagging V sub 2, I rated prime should also be lagging V sub 2 prime by the same phase angle, 36.87. We also plot the voltage across the resistive component, V sub x. So what should be the direction of V sub x? Well, this is a resistive component, so therefore the voltage should be in phase with I rated prime. So we can draw that voltage drop. So it is shown in red. How about V sub y, the voltage across the inductive component? Well, it is an inductor, so therefore the voltage across there should be leading the current that flows in there. So therefore we can draw V sub y in this manner. Okay, and we know that the sum of V sub x plus V sub y plus V sub 2 prime must equal V sub f. So therefore we can uh, draw V sub f that way. Okay. So how do we then compute for V sub 2 prime? Take note that while we know that the sum of the phasor V sub x, V sub y, and V sub 2 prime must equal the phasor V sub f, we also notice that the sum of the square of the horizontal components of these voltages plus the sum of the vertical components of these voltages must equal to the square of the sum of the magnitude of V sub f. So let's do that. So here is the sum of the horizontal components of V sub 2, V sub x, and V sub y. We square that. We add that to the vertical components of the same voltages. So these are this is the sum of the vertical components. So the vertical component of V sub x is this one, while the horizontal component is that one. The vertical component of V sub y is this one, and the horizontal component of V sub y is that one. Take note the vertical component for V sub x is negative because it is directed downward. So we square that also, the sum of the vertical components of the voltages, and that should equal to the sum or to the square of V sub f, the magnitude of V sub f. Take note that we're in this equation, we're only using the magnitudes of the phasors. So we can substitute the value of I rated prime and the magnitude of V sub f in this equation, and that should give us this equation that would allow us to solve for V sub 2 prime. So V sub 2 prime should be this one. So this is the magnitude of V sub 2 prime. But since we already know its phase angle, we can write down the phasor V sub 2 prime. Now that we know the phasor V sub 2 prime, we can rewrite the phasor equation or the KVL equation for this circuit. So V sub f, the phasor V sub f must equal to the drop in this impedance plus V sub 2 prime. Hence, we can solve V sub f. So we know the magnitude already, so that is 2400. And we get the phase angle of V sub f. Notice the phase angle of V sub f is almost zero. That's because this impedance is actually very small. Now, since we know that V sub 2 prime is 10 V sub 2, we can then solve for the voltage across the load. So the voltage across the load is approximately 233 volts. We also know I sub 1 because it is actually equal to I rated prime. Therefore, we can solve for the voltage of the or the primary winding voltage, and that should be V sub f minus I1 Z sub f. So the primary voltage, that is the voltage across the primary winding of the transformer, is equals to this. So it is lower compared to the applied voltage because of the drop across the feeder line. We can solve for the input complex power of the transformer by simply multiplying the input voltage and the conjugate of the input current. That should give us this value here. Likewise, we can compute for the output complex power of the transformer by uh, getting the product of V sub 2 and the conjugate of I rated, and that should give us this value. Take note that this represents the input average power to the transformer, and this is the output power of the transformer. So from that, we can get the uh, efficiency of the transformer, the full load efficiency, since it is operating at rated load. So power out over power in. So this is the power out. So taken from the output complex power of the transformer divided by the input power. So that will give us an efficiency of 98.6%. Now let's go to the overall voltage regulation of the whole setup. So again, voltage regulation is defined as the output voltage at no load minus the voltage, the output voltage, if the load is drawing full load divided by the voltage at full load. Now, what is the no load voltage? What is V2 if there is no load attached at the output terminals? Well, since we don't have the shunt circuit, this 200 or 2400 volts will also be the same voltage here. So the voltage here would be 2400, And we can translate that voltage at the secondary uh, by way of the turns ratio, and that should give us 240 volts here. So doing the calculation, that will give us a regulation of 3.1%. In our next video, we'll explore how to determine the parameters of the transformer. So how do we get, or how do we determine R sub 1, X sub 1, uh, R sub 2, X2, R sub C, and X sub M?